Hello, hello. And again, I have this week's Fiddler for you. This one I think was pretty easy. So if you just want, well, first of all, try it yourself. But if you just want a text description of how to go about it, I have written up a shorter version of this in the description of the video. So go ahead and check that out if you think that'll be faster and easier for you. I will go into a little bit more detail here in the video because I have more time and space, but that should give you everything you need to know. Anyway, onto the puzzle. So we have a whole number, and before I get into the f of n that they're going to talk about in this problem, I'm going to talk about like a procedure, I guess, which I'm going to call the digit sum. And so basically, if you take a number, you get its digit sum by taking all the individual digits in the number and adding them up. And this function f is going to take some number n, and it's going to apply the digit sum, and it's going to repeatedly apply that digit sum until it gets to a one-digit number. And the mapping f of n tells me how many times I had to do that digit sum in order to get to a one-digit number. And it gives a couple examples. So 23, 2 plus 3 is 5. It only takes one attempt or one procedure of the digit sum to get to a one-digit number. So f of 23 is 1. Whereas if you have 888, you need to do it twice because the first time you only get to 24, obviously not a one-digit number. You add those together and you will. And the question is, what's the smallest whole number where we have to do this 4 times, f of n equals 4, before we get to a single digit number? Now, I think it's helpful here to think about this question for smaller cases. So obviously, what digits have f of n equals 1? In other words, we have to do it one time before we get to a one-digit number. I guess but even before that, we could think of what numbers have f of n equals 0, which would just be the one-digit numbers. But that's a little bit degenerate, so we'll skip that. So what numbers do we have that would take one time to get to a one-digit number? Well, I mean, anything that sums to a one-digit number, right? So it's going to have to sum to 9 or less. If it sums to more than 9, then we're going to have to do it again. So again, I guess I have to be a little bit careful here because if it is a one-digit number, f of n would actually be 0. So this isn't quite true what I have on the screen. But basically, if we're thinking about bigger numbers, this is what we have to think about. So how do I get more than 1? Well, that's everything else, right? That's if we have digits that sum to at least 10. And if I want to think about now the smallest number, where I'm not going to go into f of n is 2 per se, just think greater than 1 because it's going to be a little bit more complicated when we get to f of n being more than 1. It doesn't divide so cleanly. But so just think, if I want a number where f of n is greater than 1, how do I do that? Well, it turns out it's got to be at least 2 digits, right? Because if it's only one digit, it's going to be, f of n is actually going to be 0. And it turns out that it's 19. So you could just kind of verify this in your head. And you would need to do 2 things to verify that. First, you have to make sure it works. Well, what's 1 plus 9? That's 10. And then I have to do it again to get to a one-digit number. So f of n is more than 1. But is it the smallest number? Could I get something smaller? Well, no, not really. Why not? Well, anything smaller than 19 is going to be a 2-digit number. That's got to be at least 2 digits, right? And so the first digit's going to be a 1, and I'm going to add something to that. And if x, so if I have a, say 13, then x is 3, 1 plus x. Well, that's only going to give me 4. If I have any number but 9 in that x place, then I'm going to get a number less than 10, and so I'm going to end up getting to a one-digit number on the first digit sum. So that would work. In the 2-digit space, now there are 3-digit numbers. I mean, there are, you can pick any number of digits, say a million. There is a 1 million digit number that has f of n equals 1, right? 1 followed by a million zeros, for example. But if I limit myself to 2-digit numbers, I kind of like to think about this um, geometrically a little bit. And if I think about all these 2-digit numbers, where the tens digit is something between 0 and 9, and the ones digit is between 0 and 9, what is the digit sum going to be? And there's this kind of very smooth breakpoint along here, where if I get to 10 or more by being kind of down to the right from this diagonal. And now if I want to think about, well, how do I actually make this small? Because this intuition is going to help us when we get into larger function value. So when I think about f of n is 2 or f of n is 3, right? When I get up there, it's going to be useful to think through this intuition now. So I have all these digits. The digits have to sum to at least 10. And if I want to think about the smallest number that does that, how am I going to think about doing that? Well, um, I'm certainly not going to pick something where the digit sum is 11, right? Because if I do that, I could very clearly do something smaller by just taking my 1th digit, decrease it by 1. It's obviously going to be a smaller number, and so I'm going to end up with a, a smaller number with the same digit sum. So in order to minimize this, I'm going to end up wanting to get to kind of the smallest possible 2-digit number. And another way of saying that is the smallest possible number that has f of n equal to 1 and not 0, right? So I'm clearly going to be something that adds up to 10. And now how am I going to arrange my tens and ones digit? Well, to make it as small as possible, the digit in kind of the bigger placement, so the tens digit in this case, should be as small as possible. That's the most important thing to minimize. And the ones digit, I want that as small as possible too, but not at the expense of the tens digit. So first I'm going to minimize my tens digit. I'm going to put a 1 there because that's the only way. I can't put a 0 there. None of those work. So I'll put a 1 there, and then I kind of have to put a 9 in the ones digit to get up high enough. And, this is just another way of saying this. What's special about this number 19? Again, I get the smallest number as possible in the tens place, and I can put a bigger number in the ones place. So let's move on and think about, how do I get an f of n of at least 2? Well, here I have to be a little bit careful, because in the old case where I said, how do I get f of n above 1? I could say, well, anything with the digit sum of 10 or more is going to have f of n greater than 1. I don't get a clean separation here like this, right? I can't say, pick some threshold x and say numbers with a digit sum of at least x will have f of n greater than 2. And just to show you why, like think about this example. I have 289 versus 999. I mean, clearly 999 is bigger than 289, and it has a bigger digit sum. But let's go through this process. Let's say 289, 2 plus 8 plus 9 is 19. Take the digit sum again, 1 plus 9, that's 10. 1 plus 0, that gets us to 1. So you have to do this 3 times, right? First to get to 19, second to get to 10, third time to get to a single digit number, in this case 1. Now what if I do this with 999? Again, it's got a bigger digit sum, but that doesn't mean it has a bigger f of n. Right, so take 999, add that together, that's 27. 2 plus 7 is 9. So it only takes 2 iterations of the digit sum process to get to a single digit number. So even though it's a bigger number, it has a bigger digit sum, it still is a smaller f of n. So we have to be a little bit careful about how we approach this. But as we described before, it will still be true that if I want to find the smallest number with f of n equals to 3, we are going to end up finding the digit sum is going to add up to the smallest number where f of n is 2, right? And again, you can just think that what if that weren't true? Well, if I have digits that add up to 19, so 19 again is the smallest number with a f of n of at least 2, then if I have a digit sum of more than 19, I can make my number smaller and end up with a digit sum of 19 and still get there. So you kind of have to minimize your digit sum. In other words, you can think of this as like a nesting process. As long as we're thinking about the smallest possible, because if we're thinking about just generally, it doesn't work this way. But if you want to minimize everything, it will end up being that to get the smallest number possible where f of n equals 2, the first digit sum is going to add up to the smallest number whose f of n is at least 1, right? So we get to 10 is the smallest number with a digit sum, with f of n equals to 1. 19 is going to be the smallest number with f of n of at least 2. And if I take the digit sum of 19, that's 10, which again is the smallest number with a digit sum, with a f of n of at least 1. And that process will extrapolate on to f of n as big as you like. So what's the smallest number we can get whose digits sum to 19? And again, we're going to go through the same process where it's really important to do 2 things. One is you don't want a large number of digits, right? The more digits you have, that number gets big really fast. And once you kind of minimize the number of digits you have, then to order them, you're going to want the digits in big places, right? So tens, hundreds, thousands place, etc. And the bigger it goes, the more you want to minimize this. You want to put the smallest digits possible there, and then you can allow bigger digits to occur in the less significant digits places. And the way to do this is actually just load this number up with as many nines as possible, which might seem a little counterintuitive. But again, the reason we want to do that is because we want to make the number of digits as small as possible. And so if I make those digits bigger, I need fewer of them to get to the right f of n. And so to get to 19, I'm going to have two nines, and then I can have one left over. And so I have the digits 9, 9, or 9 twice, and then a 1 to get to 19. Now to make this the smallest number possible, I'm just going to put that 1 at the start and follow it by nines, 199. And if for some reason you are not convinced of this, try anything else that adds up to 19. It will definitely be bigger than 199. And you can kind of prove this constructively. You can say, well, there are clearly no two digits that work because the two-digit number with the highest digit sum is 99. That'll get you 18. That's not big enough. So I need at least 100. And so if I have 100, then my first digit's a 1. And now I can add two more digits. And the highest I can make them is two nines, right? And that gets us to 19. Anything less than that, I'll be less than 19. And if I start with a 2, now my number is at least 200, and that's bigger than 199, so that's not the optimal number either. Okay, now what if I want to get to f of n is 4? Exact same logic, but now instead of summing up to 19, I'm going to want to sum to 199. So how many nines do we need to get to 199? Same exact math, divide 199 by 9, and I get 22 with a remainder of 1. Right. And so to minimize this number I get using those digits, I'm going to start with the 1 and then have 22 nines after it, which looks something like this. I hope I tried counting it. Maybe I messed it up, but I think that's right. So then the extra credit. How many whole numbers are there between 1 and 10,000 inclusive, where f of n is exactly 3? So I tried, so I don't think there's a way to do this with combinatorics. I did a little brief search, and AI is certainly not helping me out here. And then I went back to my kind of grad school combinatorics notes, and I really just don't think there's any way to do this in a reasonable way with combinatorics. As far as I can tell, and if I'm wrong, please correct me. I'd be very interested to know how to do this. I don't think that you can do something simple. I think you have to enumerate all the ways to add up to digits with f of n equals 2. And I'll show you what I mean in a second. So this is the most efficient way I could think of. And if there's a better way, please tell me. So like before, if f of n equals 3, then the digit sum, if I take the digit sum of n and I take the function f of that number, that f will be 2. Right? So to think about all of the numbers less than 10,000, where f of n is 3, I'm going to first start by thinking about, well, what are the numbers where f of n is equal to 2? And specifically, I want to know what numbers with f of n of 2 could you get to from digits less than 10,000? I mean, there are lots of numbers with f of n equals 2, but I want to restrict myself to numbers that could reasonably be added up by a 4-digit number, or I guess 10,000 is a 5-digit number. But I'm going to say 4 digits a lot because 10,000 clearly doesn't work. F of 10,000 is 1. And so it's going to be numbers less than that. And so I'm going to think about 4-digit and smaller numbers here. So if I have a number less than 36, right? Why 36? Because that's the biggest 4-digit number, 9 plus 9 plus 9 plus 9. And that's going to have, it's not just the biggest 4-digit number. More importantly, it's the 4-digit number with the largest digit sum. So I have to think about numbers 36 or less, and those digits have to sum to at least 10. Now I could go back to my little table I showed you earlier, but there's only 3 ways to do that, right? It's 19, 28, and 29. Those are the only 3 numbers with f of n equals 2 that is no more than 36. And again, you can go back to that table if you don't believe me. Now, for each of those three digits, what I'm going to need to do is enumerate the ways that I can sum to that number using four digits. Now, you may be thinking, well, why can't I do three digits or two digits? And well, you can't do two digits, but you could do three digits. But if you do that, I'm going to think of that as essentially a four-digit number with a zero at the front. So I'm going to include zeros in this process. And if a zero is in the front of the number, really, like, so if I have the number 0199, for example, that's really 199, but I'm going to think of it as a four-digit number with a leading zero because the digit sum of that versus, say, 1990 will be the same. And so the way I'm going to organize it, all these ways to sum up to these numbers, and it's certainly not the only way to do it, but I think it makes a lot of sense, is I'm going to start with small numbers and then figure out what other digits I need to add up to 19 if I'm doing 19 or 28 or 29 if I'm doing those. And I'm going to make sure that I order them smallest to largest. And then from there, I'm going to figure out how many permutations there are of that cycle. So I don't end up doing, it's almost, the solution to this ends up being almost 1,000. So I certainly don't want to do this 1,000 times. Um, we're going to do it a lot, but not quite 1,000. So for example, to get to 19, I can start with zero and then I can't put another zero. I can't have two zeros because then the largest I can get to the remaining two digits is two more nines. That's only 18. But I could have 0, 1, and then add to that 9 and 9. That's the only way to do it with 0 and 1. If I have 0 and 2, I need 17 more. The only way to do that is with an 8 and a 9. If I have 0 and 3, there are two ways to get to 19 from there. I could have a 7 and a 9 or two 8s, right? If I have 0 and 4, so I can just keep incrementing kind of the first two digits and then figure out what I need to add to get to 19 from there. And you can go through and you enumerate all the possibilities. And then once you have that set, for each of those sets, that set of four digits, there are actually lots of ways to order them, right? So 0199, that's 199, that's one number that has a digit sum of, an f of 3. But 1990 also has f of 3. I need to count that too. And so because I'm organizing this, always having smaller digits before larger digits, I need to think about all the ways I can order those digits in a way that accounts for the fact that order matters here, right? So 199 is a different number than 919 is a different number than 9,190. So, well, there are 24, which is just 4 factorial, 4 times 3 times 2 times 1, to order any set of four things. But I have to be a little bit more careful here because if a digit repeats, I shouldn't think of them as different, right? So for example, there aren't 24 ways to use the digit 0199 because the 9 repeats. So to account for that, I'm going to kind of take out the duplicates. So how am I going to do that? Well, so for example, if let's say I do 0199, that's one version of that number, and another, if the order of the nines mattered, I could switch the order of the nines. Now it's still the number 199, but if the order of those nines mattered, that would be kind of another way of doing it. And any way that I permute those digits, I could switch the order of the nines and end up with an identical number. But that would take up kind of a different ordering in the permutation. So if I have two digits that are the same, I'm going to divide that 24, that total number of ways that I can permute those digits, by 2, right? Because all of those pairs could just switch places. And if I have two pairs, so for example, 5599 is up to 28, I can just divide by 2 twice. So divide by 4, and that'll have 6 possible ways to order those numbers. If I have 3 of a kind, right? So as an example, like 1666 is a way to do this. That would add up to 19. Then I'm going to divide by 6 because there's 6 ways, 3 factorial ways, 3 times 2 times 1, to order those 6 digits, which look different from a permutation standpoint, but are really the same when thinking about the number. And I think there's only one way to do a quadruple. 7777 gets to 28. And in that case, we're going to divide by 24. There's really only one way to have 4 digits the same. And now for each combination, I'm going to count out how many really unique orderings, by which I mean orderings that result in a different number, and just add them all together. And if you do that, you should end up with 660 ways to get to 19, 165 ways to get to 28, and 120 ways to get to 29. And again, if there's a way to get those numbers of 660, 165, and 120 by combinatorics, I really want to know. Please tell me in the comments, right? But that's it. And I will post in the comments, sorry, in the description as well, a spreadsheet with all of those ways to add up to 19. I mean, that's just what I use to count these up. And hopefully that spreadsheet will be self-explanatory. But if you have any questions about it, feel free to leave them in the comments as well. All right. Thanks so much for watching, and hope you learned something. Bye.